okay. Some things I can just change later anyway.
They have They have toy model of cross-layer distributed representations.
Okay, now we're recording. Okay. Yeah, so I'll go through this, but since some other people have read the paper already, feel free to comment on stuff of it. If you
It's from Apollo
or
Research.
explain it.
Yeah, you can zoom in a bit more for the stream.
Oh, this. Okay, so I thought that the thing you linked was from
Yes.
from
this
Woodfire,
is
but this is a previous one then, right?
yeah, Goodfire is building on top of this. This is the foundation that you have to know.
Okay, so and there is also a third one that's after the Goodfire one. Is that also Goodfire?
Yeah, that's also Goodfire.
Okay, so yeah, well, I guess we can start by reading this one and some other.
I think the last one is. Yeah, I think this one and the second one is mostly toy stuff and building foundations, and the third one is actually scaling it to LLMs. I think. Something
I mean,
like
it's pretty short. Wait, is it just this short post, or is it anything else, the Goodfire one? Because then we could. Oh no, there's a full paper. Never mind. I mean, we could skim it. Let's skim the other thing to see what it is after we read this one.
45 pages. That doesn't seem short.
Yeah, no, I was just thinking because I was seeing the original, the blog post at the end and realized later that it was a full paper.
Yeah, the whole paper.
I mean, we can skim the blog post after this to see what is it, to see if we read it another day. But yeah, never mind. Let's finish this one first. Sorry if I'm coughing a bit and not. Yeah. So okay, so American stability. So first, okay, so let's go to the abstract. What is this about exactly? Because yeah, no, I hadn't seen it.
Attempt to alternative to SAE, but it's a different method, so it's not a replacement.
Attribution-based parameter decomposition. Uh-huh.
Faithful to the parameters of the original network, so I guess you reconstruct it, Require a minimal number of components to process an input, so I guess you minimize the size of the network in the loss or something, and are maximally simple.
So there is a comparison with parts encoders, but this is in parameter space, not in attribution space, right? So
that's true. It looks like that, yeah. The approach just optimizes for a minimal length description of the network's mechanisms. Is it? But does it solve superposition or something? Let's see. I don't know. We demonstrate, or does it as a side effect?
It talks here recovering features from the superposition, separating superpositions, identifying cross-layer distributed representations.
Okay, in multiple concepts.
Okay.
Yeah. So it looks like this is the initial paper, and they say problems to scale it above toy models, but apparently the last Goodfire paper has scaled it. Yeah, I think it's this last one.
Okay. People are waiting on the chat. Let me. Oh, that's just posting that.
Yeah.
Okay. So, sorry. So this is just introduction, typical Mech Interp is cool stuff, and this is why we want to do Mech Interp.
As always.
Typical paper stuff. I mean, this is important for people who haven't seen a Mech Interp paper before, but and tells you it's useful because if you are looking at a new paper from a field you are not familiar with, it tells you some papers you can read to know more. But yeah. I mean, sometimes there is new papers that we haven't seen before here, but it doesn't seem like
Yeah.
Here comparing with sparse autoencoders, even though it's a different thing. Optimizes for sparsity.
Yeah, I guess some metrics can be compared.
And leave feature geometry unexplained. Amongst a range of other uses. There's a nice review. Attribution-based parameter composition. Nice. Okay. So yeah, so we want faithful minimality on simplicity. So which is faithfulness is a set of components that sum to the parameters of the regional network. Okay, so they are not throwing up things that they think are noise. It's they're actually trying to add up to the parameter. Which is it's different from behavioral faithfulness of the circuit. Which is yeah. This is strict criterion. I wonder if maybe there's some benefits in relaxing that. But yeah, I guess if you got have a good method that has all of these things, it will be even better. It's just maybe you have a method that doesn't work that well, and you will get a better trade-off if you didn't require that kind of faithfulness.
I think this is a good point. Yeah. Behavior faithfulness does not imply faithfulness to network parameters. I think that's a good point.
Like kind of for a lot of things we care about behavioral faithfulness, right? It's just and some parts of the network parameters might be mostly noise. But yeah, I guess it's if you have this kind of faithfulness, you are pretty sure that you are not missing anything, Maybe the trade-off is better if you are mostly worried. I think, the problem with other methods that try to get the faithfulness, they don't really. They are missing it somewhere else. Okay, so attribution-based parameter decomposition. Like my worry, we'll see what this method is. My worry with methods that try this kind of faithfulness, they are going to make giant. I guess maybe there is some nice way of. I guess this is lossy compression versus lossless compression, and maybe there is some way of compressing the network nicely, but I don't know. Maybe when it's a permit, you need to throw out things that don't matter much for that.
Yeah, that behavioral faithfulness is probably like the one component of the objective function that remains consistent across all papers. And then they just try to play around with the aspect of how they're looking for either rank 1 components or weeding away the noise in the parameter space.
Wait, but no, here they are actually doing they are not doing behavioral faithfulness, right? Here they are doing actual faithfulness to the parameters of the components from to the network. Do the others try for just behavioral faithfulness then? Not sure if you understand my.
So I'm a bit confused because I mean the faithfulness aspect also ties into behavioral faithfulness, no?
Yeah.
Or do you mean it in another way?
Okay, so here, right? If you look at my screen, so there is this notion of faithfulness, right? Which is that the decomposition should identify a set components that sum to the parameters of the original network, which is a different notion of faithfulness, like is here, from behavioral faithfulness, which is like the decomposition have the similar or the same behavior as the original network.
Right, and that's what I'm saying. Like when I think when you go for this version of faithfulness, you do to some extent get behavioral faithfulness in the sense that the components themselves are still ideally the ones you find. And in this one, I believe they use attribution to find the top K components before looking for or before doing the faithfulness approach. So it's still, you're ideally still like getting a network that faithfully parameter wise is a much smaller set, but also to act in the same manner.
I guess we can also look at this image. So we have the weights and they flatten them. Okay, makes sense. But like for each layer or for all layers, whatever, we'll see. So they decompose it with some method and they get a sum of whatever this is. Yeah. Minimal was which component is possible. Seems like there is a trade-off between minimality and simplicity. I guess you can put the whole spectrum. Like if you want the maximally minimal, the composition is just the flattened version, just the actual thing. I guess you want also simplicity. Second list it seems like you want like simplicity of the decomposition and they need two different things because of that. Because they are doing that of each component, but yeah, never mind. Okay.
When it's replicating the behavior, when it's decomposed, do you just sum the outputs or something?
No, it's so it's replicating the network, like the decomposition is like in this paper at least seems to be like lossless compression, so it's like or analogous to that in that this is decomposing, but when you add up all of this, you should get the same weights.
Yeah, and when you are evaluating the decomposed network, so all the different subparts, do you like run input through all of them and then sum it all up, or when you're like evaluating the behavioral aspect?
No idea. I
Should I
haven't
read
gotten
more?
that part yet, but my guess is that you will just get the same output.
Yeah, I would expect that probably as well, yeah. And are
I
the
was
different
thinking about how
parts interpretable? Are the different decomposed parts?
I mean, the
Yeah,
idea
that's
is
my
that the
question.
decomposed parts are interpretable, but I don't know if they are. We'll see.
Okay. I don't see why a priori it should be interpretable, so...
They are trying to decompose it in a set of parts that are simple and minimal. So, meaning they want to decompose it into a small amount of parts that have that each of them are simple, like have are simple, computationally simple. Seems to be that this should work. There should be a version where you just try to find the simplest decomposition and you have a notion of how simple the decomposition that just combines these two things. But I guess that you can also just have two parameters for one parameter for each and have some trade-off.
Yeah, and then the search for the hyperparameters, which was one of the issues that they kept running into, then becomes like the thing you have to mitigate, right? Because if you, depending on how you set your top K, if it's too large, then additional problems creep in, right? So you get component mixing or mechanism mixing, versus if you set it too small, then you never actually find a good small set, right? And this is even before you look for sparsity and simplicity.
Mm. It also feels to me that there should be some way of writing how complex a decomposition it is as opposed to each component, how computationally simple it is, that just automatically does the trade-off. And like I think there is some trade-offs here you cannot do, where maybe there are some part where you make a slightly you have different levels of, I don't know, it's hard to think about. I need to look at what the actual function is, but we'll see. Okay, so is for its parameters. Yeah, so for a single input, for any given input, number should not require this mechanism simultaneously, which makes sense. So sorry. Es que Okay, so yeah, so how does this attribution-based decomposition work? Is the question. So yeah, they have mechanisms, vectors in parameter space. Makes sense. So this is like this is a linear method of parameter decomposition, right? If I understand correctly.
Linear.
Yeah, it falls under that umbrella.
And that makes me wanna look at the examples in the newspaper, what exact interpretable things they found inside.
So they're just so you're just dividing the weights as a sum of vectors or in parameter space.
Ooh. Okay. I'm just quickly skimming the last Goodfire paper, and it does seem like every rank 1 parameter component, like every decomposed rank 1 parameter component, like corresponds to something interpretable.
Nice.
Like proper nouns, names, and rare words, biology and medical research terminology, just like SAEs. Interesting.
Are they also have they made any paper looking for manifolds in parameter space?
Thank you for an idea. I'm writing that up. Yeah. I'm not sure how you would make this into manifolds. Maybe you could just. What if you cluster? Did they do that? I don't know if they did do that. You could cluster the different rank 1 parameter components and see if they form a shape. That's what I wanted actually. Like, because I was thinking if you could cluster the activations as you run them, but the issue is okay. I'm not sure.
There are already papers of wood-fire papers where they cluster activations to find manifolds, right?
The primary one is the but you have to start with something that you know already, so it's not really unsupervised when you're collecting the activations. So they solved it by clustering SAE features, which are unsupervised. I was thinking if you could, instead of clustering SAE features, just get all the activations that correspond to all the different SAE features and cluster them directly, but because of superposition, that will be more messy. So I kind of want to compare manifolds of that you get from clustering SAE features versus clustering activations.
Yeah, I mean, the problem with clustering activations is that SAE features are components of the activations, where the activations are like the whole thing, which includes a lot of things.
Yeah, exactly.
So yeah, it's not the same kind of thing they're looking for.
Yeah, there will be more like mess in
But
there,
if you did something like that on here, on the the vectors here, it would be more like the sparse doing it on the sparse encoders.
Yeah.
Like, you definitely cannot do it on the weights here because the weights are a single point in weight space.
You can collect like they had to somehow figure out what the parameter components correspond to. So my guess is they just ran activations and found what it correlates with. So I guess you could just take the rank 1 parameter components, just like and cluster the activations that you compute from them, just like you cluster SAE features. That would be my guess. But maybe they try to do that. Let's see. Minimality ensures the decomposition compromises specialized components that play distinct roles. Ah.
Okay. Anyway, going to how the method works. So they have this APD, they want to decompose it in vectors, and so they optimize for faithfulness. So they decompose the network parameters into parameters. Number parameters. Oh, wait a moment. I'm going to download the PDF briefly. Let's take a bit. I should have done that on a different screen, maybe. Like a different. I'll just do this. Anyway, sorry. Kind of going slowly today. Let's try go back to what I watched. So they have the neural network. They have the parameters. And they have a set of components. So the parameters have like so it's they say they flatten it, but here it's seems like it's actually a matrix with you know layer and 2 dimensions. No, L de networks with matrix, so it's network models.
Do you wanna zoom a bit?
I don't know what the yeah, there was a common of each network. Yeah.
Yeah.
So they are trying to minimize. Also, yeah, I'll close this. Sorry. They are trying to minimize the they're trying to minimize mean square error with respect to the target numbers parameters.
Mean square error, so
the so this is not
the sum. Yeah, I see the sum mean square error.
Okay, so this is not, as I thought, this is not actual perfectly faithful. It's just trying to approximately be faithful. We want to estimate the causal importance of each parameter component.
Oh yeah, they also show that in the original image that the parameters approximately equal the sum. Yeah, wiggly equals approximate.
Yeah, and that's even if you can say you trust the attribution method in terms of the issues that come with just naive attribution in the first place, or naive attribution-based approaches in the first place.
Can you elaborate? If you want.
Yeah, sorry. Wait a moment. What's that? Is that there? Or so what did you say? Sorry, I missed that.
Oh no, I said that's even if you can trust naive gradient attribution-based methods in the first place.
Yeah.
And that's like assuming you can get the hyperparameters proper and so on and so forth.
Yeah, so yeah, here they are doing attribution to try to so they do attribution to try to find how important. Yes, and just they are just using attribution methods. Maybe the other papers do better things. So each component, how important it is. Yeah, gradient attribution. Because you can't do attribution in the you try all possible combinations ways, but that's just not that's just intractable for big networks. So yeah. On a forward pass with the target model.
I see.
Okay. So what do they do with the attribution? Okay, so they do top K on the most attributed parameter components. Perform pass. And they train the output of the top K most attributed parameter components to match the target network's output by minimizing el minimality. Distance of divergent measures. So yeah.
Wow, this math seems so much clearer than some other papers where they put too much complex math unnecessarily.
So
I feel like
I'm confused because so minimality is trying to use the as few components as possible, right? Why is here the loss? Why is here the loss of minimality? Some distance, or divergence measure.
I think it has to do with the singular value. So they try to use that as the way that they get the simplicity. And you can't do gradients through that step or something of that nature. And so they needed a norm to be able to add a trick to get around that.
But why is this loss? Like, wouldn't the minimality, since the number of components, be just the K of the top K, or am I missing something? Okay. I think I'm missing something. So I think here is when they say minimality. Maybe I think I was reading it wrong because it's a few components as possible. No, I was components reachable. No, this is maybe it's the number of components. Yeah, I'm still confused. Like I will guess if it's the number of components depends only on the K of the top K. So match the target's network's outputs by minimizing. It's just okay. So this loss minimality. This is still this is the still the difference of like they're just training them to be similar, but it's weird that they call it loss minimality. Why is this measure some other measure and not also mean square error? Whatever. Yeah. Maybe because it's H components. I don't know. These strange steps change the active parameter components to better reconstruct the targets. Maybe. to better consider the target network behavior on a given data point. So they train on each data point to match the behavior. They were saying that they were using a different notion of behavioral faithfulness. But here it seems they actually optimizing for behavioral faithfulness, which is okay.
Because the importance.
But the typical components on the data. In some cases, we also train some of the hidden activations to be similar both for all passes. Since it may be otherwise possible for a PD to learn solutions that produce the same outputs using different computations. Why? In some cases, when? Like, is it just random or?
Yeah.
I don't know. There's some things. This method seems like maybe overcomplicated and like has a lot of weird steps and stuff that. I don't know. It just feels like there should be a better method to an easier, simpler method to decompose.
This is like when I'm reading there that it would like in the attribution step it would, if you wanna calculate all the attributions, it would involve large number of causal interventions. That's interesting. Since yesterday I was like a bit into attempts at
oh yeah, but that's just in general, like
issues.
I mean that's in general. That's why people came up with gradient patching and that kind of thing. The gradient attributions. Using gradients to approximate attributions because otherwise it becomes. But that's been known for a long time in Mech Interp, like a few years.
Yeah. I'm observing the parallel with causal deep learning, which is also like if you wanna do that ideally, you will have also interactability basically. It seems like rediscovering the same things, or analogous at least things.
Yeah, I'm going to.
Looks like gradient-based attribution methods are also older than Mech Interp in the explainable AI era. Interesting.
Nice. They are not. It's not that different from just the idea of gradient descent.
Yeah.
In gradient descent, you are trying to do gradient-based attributions on which parts increase the correct answer and the update on them.
Yeah.
Or you can see it that way.
Just approximate everything with gradient descent. That's how you solve all the life problems.
Linear approximation. It's proposition. Yeah. Okay. So they. So they do all of that. And then they just use patch top k to set a feasibility parameter comparison for the millimeter step. Okay, so are there two top k's then? There is top k most attributed per programmer, and then they are doing top k on the components, so it's less, less do sparsity on the.
Saliency. Yes, that's the original. Okay, I'm rebuilding into gradient-based attributions. Maybe not worth.
Attribution
but
step.
saliency was one of the OG methods in
Vision for simplicity.
explainable AI.
I feel
before
especially
Mech
weird
Interp
that we're just
existed.
doing gradient methods but on the input, and that was kind of
Yeah.
meh.
Yeah, basically.
Because actual outputs on complicated network that maybe works if you are doing something very simple. You have, I don't know, some very shallow MNIS calcifier or something. But in a real network that is doing anything interesting, the output is going to be some complicated function on the input, and it's only going to give you sensical answers in very specific situations. Like,
Yeah.
there's not useless, but yeah, I don't know.
Then take into account mechanistic aspects. Attribution patching approximates the whole sweep with Taylor expansion. Okay. Thing.
Okay, so yeah, anyway, so automation for simplicity, I was getting that, sorry. So components are also trying to be simpler than the parameter staging network. We would like to penalize parameter components that span more ranks or more layers than necessary by minimizing the sum of ranks of all matrix in active components.
I do wonder if they could have predicted a lot of the hurdles that they end up running into taking this method versus maybe why they didn't just go to SPD to start off. But I don't know. I think maybe I might be biased after at least reading both and then coming to that conclusion versus like if you had to start from scratch, what would have been the first step to take? Possibly also as a sanity check before going to other methods.
I don't know what the other methods are, but at least my take on this method is that it seems like overcomplicated, that it has a lot of details, and like maybe a better method will just not be a simpler thing.
No, it gets more. I mean, they simplify certain parts, but for the most part, for example, VPD's objective function is there's a lot more components in there because they're doing a lot more things like the adversarial aspect as well too. But at least like the main like thing that they distanced themselves from was using this attribution based approach versus SPD. I think they train some MLPs to predict or to try to get a better intuition of causality. But then there are additional tricks that they had to do there in terms of, well, how do you determine what your minimal set is, so on and so forth.
I mean, we can check the limitation section, and you can tell us like how much that matches things that were fixed on future papers. Yeah, the attribution method is also right. Is like the naive way of doing things, and it seems like they could have guessed that there will be some. Well, it surprised me that there's something on limitation section about that.
What exactly are the limitations you said? Do you think?
I think Eric was thinking about how they do, apparently in the other paper, they do this attribution part differently. For example, to try find better notions of causality than just doing gradient descent to approximate it linearly, which has so much of problems. I mean, thinking that it wouldn't surprise me if in the limitation section they already realized this, but I don't know, I haven't gotten that part yet. I don't know, it still feels to me like, if the other methods are still very complicated, it feels like, okay, so all of this is more complicated than sparse encoders, and it feels like, at least the base sparse encoder, right? And there are other versions that have some fancier things, but it feels like I just want some nice, simple method that doesn't feel hacky, that where you just do some optimization directly with a loss with a few components, and it just works. But I don't know, maybe there is not such method. Feels like there should be. But I
think I didn't quote exactly method like you mean alternative to the attribution or
I feel like there should be
some
some. No, I mean in general, the whole paper. There feels like there should. Maybe I'm wrong, but it feels to me like there should be some simpler way with a lot less steps of decomposing the networks in a simpler way. Maybe it works better, but like, is this really the kind of thing? Like, this feels like very complicated for being like the first thing you try, right? If I was trying, maybe it turns out if you try something simpler, it doesn't work. But I don't know. For example, it feels like to me like simplicity and minimality are related, and there is surely some way of decomposing where you are optimizing for both at the same time, where there is, you have some notion of, I don't know, how complicated the decomposition is, where you try to make the simplest decomposition, like, where the model does the trade-offs.
Yeah. Like minimal description length should have both simplicity and minimality. But yeah, this is different in a way. Yeah, I see what you're saying there. I think, like that's the first thought I had. Like simplicity and minimality seem way too related to be disconnected like this.
Like, I guess a problem with that is that if you only optimize with some notion of simplicity of the decomposition or something, maybe the simplest decomposition is just the original model, you know? Or maybe, you know, all ways of decomposing that have the same that are equivalent to the original one have the same simplicity, in some sense. You are just doing a trade-off between how many components it has and how much. Yeah, I guess you could just fix it to have few components, but yeah, then you have two, whatever. But components also try to be simpler than the target network. We would like to penalize the parameter components. Also, I see user is writing, but I'll look at this first while you write.
Yeah, I think I think it's just embedded in the fact that determining causality already is a difficult problem. So it just compounds here where you're trying to do not just causality, but additional things. So you kind of can't really, I guess, get to a simpler method. But
I feel like a simpler method shouldn't require thinking about causality. There should be methods that don't require thinking about causality. Like, in the activations version with sparse encoders, we don't go doing anything like trying to determine causality from sparse from the activations or whatever, right? And we still decomposing but I guess maybe you could imagine a method that also does that on the sparsed encoders. But yeah, I don't know.
Yeah, but this is like this one is minimum. You're looking for I guess minimum computation, so it's different than I guess the feature space, right? So is there a simpler method of finding an equivalent computation that will give you similar results without trying to at least figure out the fact that the minimal version is causally equivalent or something, I don't know, to the more complex one. So that seems like just like a harder problem in general
Yeah.
to try to resolve.
Okay, yeah, I think that makes sense. So I was thinking, so the problem here is that, okay, we don't just want to decompose. There is a lot of ways of decomposing it. We want a way of decomposing it where in some sense its parameter matters. On the activations, we are assuming that instead of doing all of this causality stuff, we could do all of this causality stuff on the activations too, and try features that are causally important for the thing. Maybe that's a paper, or maybe people have already done that. But in the activations, instead, you want to you just assume that the sparsity works. Like if you divide the network in a series of sparsity. Yeah, of sparse. Yeah, you decompose the feature. Some set of sparse features that to compress the activations that will get you the causally relevant ones. But that maybe doesn't work in activation in parameter space. I mean, you could, I guess, try to. Yeah, okay, so I guess the thing with activation space is that in activations you have a bunch of activations and you can do sparsity on each activation. But here the problem is you just have a single set of weights and you have to do, you could still, I guess, do a sparsity of making weights, a set of weights that only where only a small percentage of the weights are used for each thing, but I don't know if that makes that much sense.
It's also possible you end up with a different kind of architecture if you solve this. So that's also another like sideways segue kind of thing.
Also, I feel like if you can actually do the way I was thinking, you will have a thing that's maybe more efficient because it's already has some nice sparsity and you can just run that to get the behavior of the model using less computation.
Can you summarize your methods that you told?
I think my method is too vague to work. It's just something vaguely like doing something like sparse, doing some sparse weights decomposition where you only use some small percentage of the weights for its activation or something.
I guess you could cut off when you do the sum. You could like make it just 90% enough.
Here they're kind of trying to do something similar to that, but they are doing it by doing attribution to which weights are more important for some output. You know, this is this method is kind of similar, but they are doing it with the causal stuff. Just feels like you should be able to do it with just sparsity and reconstruction laws, like the size do it. You know.
Caleb wrote in the chat like a mixture of experts and essays.
Yeah, kind of.
Interesting.
Like
mixture of expert essays.
Here they are doing minimality trading instead. I guess if you you could also do this method and ignore the minimality part if you ignore the simplicity part if you wanted to Well, no, not really. I just feel like there should be a, maybe I'm missing, yeah, maybe this doesn't make sense, but I feel like there should be a method, it should be possible to make a method that just does this kind of decomposition in like a single step of like, you have a bunch of examples and you try to get the same behavior with some sparse subset of the weights in weight space or something. Where you just have, I don't know how the laws will work, but it's something where you just have the mean square error on the reconstruction and some sparsity thing like in the sparse encoders. I guess here they're doing something like that, but the sparsity thing is top K most attributed. But I guess this is kind of already this thing. It just feels like the way they are doing it is over complicated. Maybe I'm just missing the ways where when you try to do that, you realize that this doesn't work because some reason, and then you add the next step and so on, right? Like maybe you try to do that.
They have some sparsity penalty in the simplicity part, maybe.
So they do sparsity in that they do top K most attributed parameter components, right?
We sum only the top. Oh, that was my idea. But okay, I see.
Yeah, and then they do simplicity, which is on each of the components they try to make it have less ranks.
Okay. That's the
so
simplicity
they're
part.
just doing the.
Yeah, that makes sense.
Some of the rank material components. Yeah. They do so they just minimize the norm of the singular values for whatever. Yeah, weight madness using Why? I'm curious. Why do this instead of just do the usual? I guess they just actually want less ranks. Normally, people use implicit when people implicitly for simplicity of neural networks they do like the norm. You know. But here they do this other thing. I'm wondering why. Okay. Also, I'm not sure I understand the thing Usagi wrote where he said, and maybe we consider simple case multivariate variable regression, which is WX, W is weight, which is input. We decompose W into rank 1 matrices and it become single variable regressions. Yeah. I guess that makes sense. Okay, also they are not decomposing the network biases. Anyway.
Did they explain already how does the forward pass through the decomposed model looks like running input through all the decomposed parts and summing the results, something like that? How do they measure the reconstruction loss, basically? MSC, it has to sum.
Oh, the reconstruction loss.
Do they ever?
They just do minimum square error.
Yeah, they don't work with activations ever. They only work with.
Oh no, they do.
The parameters.
Yeah, but they do on the attribution step. They are working with the output, so they do a forward pass for that.
Yeah, and how does the forward pass work though?
Do
you put the input into all the different decomposed parts, and then you sum the output or something? output.
Okay, I get what you mean.
You said you don't get what I mean?
Yeah, I think I get. I get it. So it will be. So this is a sum of the. Yeah, I think it's just so. This is doing a sum, and this is the parameters. Yeah, it's just doing a sum of the parameters, right? The formula is more. So this is like the doing the gradient over the sum over the sum for each layer and each row and column, and
okay, yeah, this makes sense, but this doesn't work with activations. No, this is just over the parameters. Oh wait.
No, but it's this is x is the input, so it's.
Oh, I see. Okay.
Yeah. So it is doing the. I just adding them, I guess.
Okay.
And I this idea is that when if you the decomposition, if you add the parameters, you get the original doing.
They sum the parameters.
Yeah, they sum the parameters and they.
So they first sum the parameters, and on the summed parameters they do the forward pass. Okay. For an input x, you select the relevant components, construct the vector depending on how attributed it is. You sum that all up, and then you run a normal forward pass.
Because
through
also
that and through the summed architecture. Yeah, makes sense. Okay. Yeah, now I'm not confused.
Oh, I guess, yeah, so here in this formula, like this, a sum over the layer and the row and columns, but there is like is multiplied by p for the all each of the components, so that's still the same as summing it up, all of them. Okay. Also, it does here that the parameters are supposed to be the sum of the Okay, so there's the methods. So they do the attribution, and they get this, and then they do the minimality, and then they do setup k. Second for pass with the parameters and the input situations. So on this method, they are doing a lot of computation. So they are doing. They have to do a forward pass for the attribution space, and then a backward pass for the attribution, and then a forward. They don't need to do the top k most attributed parameters, and do a second forward pass and a second backward pass. So you are doing 2 backward passes per thing. So this is like worse than training a network. Paperless loss. So translate losses. Minimality loss. Simplicity loss. Penalize promise compares spam more ranks, so more ranges than necessary. Okay. So they use some toy models and they find explanations from them.
I should have just read one more sentence. I just wrote here that we sum top k attributed parameters using a parameter vector. I use it to perform forward pass. I was trying to answer literally what was answered to me in the next sentence. I would have read. Oh my god. You just read paper before guessing and trying to figure out.
Yeah. But the thing is, you do the sum and you have the sum in the in the graph for the gradients. In PyTorch, you can just do it over the gradient over the sum nicely.
Yeah.
Still get for each component. Even if the thing you are actually multiplying is just next step. The added thing. So the two model as superposition. Where we have the ground truth. Okay, so they have a bunch of here in the superposition one, which is a kind of a weird example, but they find that the way the composition finds components for each of the components of the matrix, which okay, makes sense. It's a weird sampling that the toy model superposition is supposed to be a toy model of the activations stuff. But I guess this is the weights version. You take with train weights that represent the activation should have some components that match to each direction in the activation space. And they just find them.
There. Yeah.
In
order to have superposition activations, you should have superposition weights. Minimizing minimality.
Yeah, so there's a lot of things, but this is, as I understand, it's mostly saying that they.
Oh, you can use scale divergence instead of MSE loss. I guess that works as well. But they say that in the appendix for the minimality.
You should just look at the nice picture instead of all of that. So tell me if you feel like I'm going too slow or something, or you want me to look at some specific thing, or you want to just try to explain something yourself or something. I feel like I'm kind of being a bit. I'm kind of
that guy
not
left.
super
I'm even slower than you, so it's fine.
slow today.
Yeah.
Because I
also
think I sleep too much during the weekend for a bunch of reasons. Well, a bunch of reasons that it's too hot.
Oh yeah, makes sense.
But yeah. I'll ask you later about maths, but let's not get distracted now.
Yes. No, this is relevant to maths basically for me. So
But yeah, I hope you did get maths work done after you left the call yesterday.
say again?
I hope you did get maths application stuff done yesterday after
Yes.
you left.
Yeah, I finished the one research test, yes. Things left. Okay, this step trains the active panel components to better reconstruct the target network's behavior on a given data point. Yeah, I see Albert is targeting Matt because he's not here. Yeah.
Understandable. You can do
but
that after the reading group.
Yeah, I should have thought like Rambert because he's targeting mainly Apollo, I think, and this is an Apollo paper.
Yeah.
I mentioned that to him.
Okay, well, anyway, trying to get illustrated, going back to the image, which maybe is easier for me to read despite being kind of not super awake right now, is
so yeah, you can imagine this thing here with the superposition, toy model superposition that is
okay,
here.
so they have
when they do more edits and then apply like to the architecture and apply to LLMs, it seems like it also reconstructs interpretable features like this in the newest Goodfire paper.
Yeah, I guess it's also because I think a problem with this one is maybe too expensive to do in LLMs.
But they still did it, so.
Yeah, no, I mean the other paper is like I expect the newer papers have maybe the use are more efficient or something, or maybe they just spend a lot of money.
So if you look here, wait, in the okay. So do they decompose each weight matrix on their own in this paper? Or do they... No, they first put everything together and then they... Okay, so like... so here they first append all the matrices together and then they decompose those, right? The whole whole giga matrix when they put all the matrices together.
Yes.
So if you look at the new Goodfire paper, I just posted a screenshot in the chat. You can see that they decompose each weight matrix separately into the different components. So that's a difference.
I mean, here is still here. I think it still has rows and columns and like it still has the right dimensions to decompositing everything, but they are just not doing the optimization on. They're just doing the optimization for everything.
Yeah, they do it for the whole network. Because at the beginning they do the appending
But they still have the same. Yeah, but they still have the same. You could still plot graphs like the ones you see there because they still have the same amount of weights and they
Okay, that's maybe true.
You can still each weight still has its layer and they are just for the purpose of the optimization, not.
Okay, maybe it was still trained the same way. Yeah, that's true.
So.
If you want, do you wanna check the new Goodfire papers? They have just one visualization there that's relatively short to look through on the LLMs.
Okay, we can look at it at those.
You're looking at.
Yeah.
So if you open this last page, last link.
So this one.
Then you can click on the different weight matrices on left, and here you can just scroll and see the different corresponding something like SAE features.
Oh, cool. So what is do you know what this measure is? Right? Like I understand what feature activating on something is. I'm not sure I understand what a parameter decomposition component activating on the. It's an attribution method like the others. Like you
Probably.
check that this parameter causes
this component.
That output.
This component frequently fires. So my guess would be how much, what's the total size, like what's the total length or something. Like they have to quantify frequently fires. So if the parameter, if this row length
maybe
matrix
it's something
doesn't
like
contribute anything.
SMLP, so I think it's maybe something like related to the causality, that this is causally relevant to the thing, which they calculate in some way. Eric said about something about MLPs.
Yeah, Rambler joined when I mentioned it's an Apollo paper. Yeah, just for context, Rambert, this is an alternative to SAEs, which apparently originates from Apollo, which I didn't know.
It's
and
not
then
alternative to SAEs.
on top
It's
of it
on
and scale it to LMs.
Instead of SAE, this is not alternative to SAEs because this is on parameters instead of on activations.
Yeah. Okay. Yeah. It's it's a different method, similar to
it's
SAEs,
trying to do parameter decomposition, like take the parameters and decompose it in like a bunch of subcomponents that do independently useful things.
Yeah, it is not replacing SAEs. Yeah. Can you use it for steering though? How? Okay, so I have multiple questions. Can you use it for steering? How much monosemantic it is compared to
send
SAEs?
the paper to Claude and ask it to Claude.
Can you do hybrid with SAEs?
I believe with SAEs, I'm not sure what you will do because they are doing different things, right? Like you could do something closer to an SAE the way I was thinking. I don't know if that makes sense, but yeah. Also, by the way, going back to the paper, it seems like they just have the compositions, and each has a bunch of components, and each component seems to correspond to each. This is on the toy model of the superposition, to each of the superposition components, and that makes sense. I mean, this works because both things are linear, because it was a toy model where they're assuming that it is. So this doesn't tell us much if it works on real networks.
Or can you say again the point that you made? This doesn't
this is just the toy model of superposition. So here it seems like it works. But that doesn't tell us much because it's a toy model of superposition where everything is linear and specifically represented in some way.
So they did some fixes and now it's scaled to LM, yeah.
Yeah. They also do toy model of compressed computation. Yeah, so yeah, they do this. The components are very similar in whatever measure.
What does compressed computation mean compared to superposition?
I think this is mean max cosine similarity. Okay, yeah, that makes sense. So numbers you get components that are cosine similarity are similar to the actual ground truth thing. So yeah. Whatever the sample. More computations that has neurons. Very compressed computation. So this is something like superposition, but on the weight space, maybe. Yeah. Oh, from 10 to 22 is pretty big. It's pretty old. 22 is like prehistory Mech Interp now.
Yeah, that's true. Yeah, I'm not sure if I said it, that I found that the gradient attribution methods predate even Schmidhuber's golden era, so he cannot say that he invented it.
Who knows, like maybe as a student at some point he published something on some...
Yeah.
In the margins of some homework he...
It's some lost note. Just like all the people in
I have a method to solve it that doesn't fit on this margin.
Out of the scope of what he could publish before.
Respect those models solution to this time depend on sparsity of input as model. Okay, so they try to look into this, but it turns out to be more complicated. Feature work.
So when you sum only the top k most attributed parameter components, this makes it that the other ones can encode some irrelevant noise, which you can throw away, I guess. Is my intuition there. Which you increase the attribution of active components on the data. Maybe this also prevents feature splitting. Yeah, is there like something like feature splitting? How big is reconstruction loss compared to SAEs? Is there something like feature splitting duplication? Does increasing number of...
I'm curious, what did Claude answer to your previous questions, though?
Yeah, I might put all those questions into GPT Pro, actually. I think that's better than
Pro,
Claude,
yeah.
but yeah. But both are good. Maybe once Fable is alive again, then it will be better again.
Maybe they lost their chance and now they'll have to compete with OpenAI's new models and whatever.
Oh yeah, this week should release GPT 5.6 according to all the leaks, which might be completely wrong.
I mean, maybe that will change because of the whole,
Someone leaked that they were A/B testing it, and there were implicit guardrails. Like someone was discussing Siamese twins, and the model said, "We're taking more time than before to do safety of this prompt," or something like that. So it seems like there will be similar guardrails on GPT 5.6.
And then someone will say that they found a jailbreak or whatever, and then they'll...
I don't think that will happen, but yeah.
Probably not. That point would be too silly.
Yeah. It's too much liking the government compared to Anthropic, I think.
Yeah.
Well, whatever. Yeah, let's not get distracted, maybe.
Yeah. Okay,
What I wanted
so
to write, that's increasing number of, what's the word for the components? Components of the rank 1 components make the quote unquote features more sparse, more granular, like in essays. I would expect that's true. Like I would expect a lot of these things would be shared with essays. But I wonder how compared to essays. When they compare to essays, I wonder what all comparisons they found. Also, cross-layer transcoders. Okay, in some cases. Okay, I'm also curious about the toy model of cross-layer transcoder distributed computation. That sounds interesting. Like, how do they toy modelify that? These toy models are like, I don't know. It's like those beautiful mathematical proofs on the cases that are trivial. Then you go into the real world and everything is messy, just like with LLMs.
yeah, all of this paper is just testing on toy models.
Yeah. Or
But
idealized physics examples. It's similar.
yeah, very simple toy models that are also kind of have some of the assumptions of this thing baking, like it's some linear decomposition of the thing or whatever, you know.
Yeah, that's true.
But apparently it
It's
works
like,
with slight changes. It works on the good, on the lamp, so that's nice.
it's like in physics, like assume cow is spherical and has no friction and stuff like this.
And then you test your method on actually a spherical cow.
Yeah. Actually, when you do the toy model of like,
Sorry, can you repeat that?
yeah, when you do the toy model of like sphere and you wanna learn a circle, toy model of a circle, that's technically a spherical cow equivalent, basically.
No, I was annoying my physicist bioengineering a spherical cow just to run. We ran this experiment, it matches our model's predictions.
Yeah.
This is like kind of what they're doing here.
Yeah. I mean, it makes sense. It's a good starting point, and then you have to apply to the real world. It gets messy, and you have to do all those corrections. In physics, you have perturbation theory, which starts with simple, and then you have to add all these higher order corrections. Standard model uses that as
To me, I
well.
still feel like the method is, even for working on the toy models, feels like, do you really need all of those steps? But I guess you probably do, because you need to optimize multiple things, but still, I don't know.
Say again?
Like, I guess you probably do, because you need to optimize for multiple things, but something about having a method that has, like, two different steps where you are using, like, different losses, and you do two forward passes and backward passes on the model.
Probably do what?
Maybe like there should be a simpler method, I don't know.
Okay. They didn't minimize the simplicity here enough. They didn't optimize for simplicity enough.
Maybe I'm just wrong. Like, it seems possible to me that I'm just wrong. It's you do need here what we actually want requires, optimizing two things at the same time, like simplicity, but also having multiple components, but not enough and whatever. But still feels that there should be some lost term that you could use where you just optimize in some way, you do some simple optimization and you get the right thing on a bunch of examples.
I wonder if I ask ChatGPT, is there a simple way to do this? If it will say something that's not slop.
Maybe you need to wait a week until the new ChatGPT is out.
Yeah.
And this last week there haven't been a lot of since big AI news, right?
Say again?
In the last few days, there hadn't been any big AI news.
Weeks, you said?
Days.
Days. Yeah, AI winter confirmed. Pack your bags. No Singularity is cancelled. Yeah.
I guess people also, people are probably also getting ready for all of the conference deadlines and all that.
It's also summer as people are having summer breaks. Well, not really, because GPT 5.6 should be released right
Yeah,
now.
no AI people
So,
will not take some real summer breaks.
no summer break for you.
Or maybe they
wonder
will,
if
and
that-
then will suddenly will have like the singularity when they will come back. But yeah, anyway, so yeah, there's a lot of details here, but I don't know. It's been a while, and not that interested, I guess, on the details. If we are also want to read at some point the other papers and they are better, we might as well just.
So I'm confused a bit. Oh, so minimality is defined as the distance.
Yeah, I'm
Isn't
confused
minimality
by
the
that.
same as reconstruction loss?
No.
Or something?
Okay.
Wait.
There it's kind of reconstruction loss, but they call it minimality loss, but this seems to be something like a reconstruction loss that they do after doing the top K, and they just call it minimality loss because it's trying to increase the reconstruction, or they try to
I
increase the
see, I think I
reconstruction
see.
after you do top
Yeah,
K.
yeah.
You know?
Yeah, okay, that makes sense. Yeah. So,
But this, I think it's a bad name because it's not a loss that encourages minimality. It's just a reconstruction loss that you use after doing top K to try to make the remaining components be the full thing.
okay. The faithfulness is the sum is trying to minimize mean squared error with respect to target network's parameters. So that is the reconstructionless part, the faithfulness part, right? And the minimality part is you want as little components as possible to have you want the reconstruction loss between top K components according to the attribution and the original model. So
Yeah, and
it's
the output of the
it's
original
minimality.
model.
Yeah, so it's minimality because you want minimal amount defined by top K.
Yeah, but the minimality part is not all the losses in the top K.
Say again?
The minimality part is not on the loss. The loss is just a normal main square, reconstruction loss.
Yeah.
The minimality is just the top K part.
Yes.
I was confused by that earlier, but I think I understood it.
Yeah, I was also confused, and I think I just grouped it.
I think it's just a bad name. I think it's just a bad name for the minimality loss.
I think so.
It's a reconstruction loss on the minimality step, basically.
The reconstruction loss on minimal.
So there is a minimality training step, and this is just the reconstruction loss on the minimality training step. And the minimality step is just doing top K and then doing, optimizing for reconstruction loss. Which, whatever you want to measure it, some distance, which can be KL divergence or whatever you want.
I feel like you're dividing it into two things that I'm not sure if that's
there is a minimality training step and attribution step, and they are different, which is that feels overcomplicated, but okay.
Wait,
And it's doing two, like a backward, like a forward pass and a backward pass on each. Like there is like two optimization steps being done here.
You first approximate the attributions through gradient attributions.
Yes.
Then you use the approximated gradient attributions to find the top K most attributed parameter component. Then you sum those, right?
And you then, on some examples, try to maximize reconstruction loss on those top K ones.
Yes. In some examples.
Yeah, it feels to me that there should be some method that only has one step, where you...
Wait, I'm a bit confused still. Wait. There is optimizing for faithfulness, where you sum everything, and then do... So loss faithfulness is the whole reconstruction loss.
Yes.
No, that's only the parameters. Loss faithfulness is how different are the parameters, MSC. So you don't run any forward pass. That is only looking at the weights. Attribution step, you run training data through, get the attributions through the gradient attributions, then get the top K most attributed parameter components. You sum those? Do you sum them? I don't know. You have to probably sum those. Then you run the forward pass on those summed top K attributed parameters and do a reconstruction loss with the original parameters of the model.
You also optimize for simplicity.
Yes.
I feel like this is doing a lot of separate optimizations.
Yeah, there's also written, in some cases, we also train some of the hidden activations to be similar on both forward passes. What?
Yeah, I feel like this is this method seems super
It sounds very duct taped. I think I see your confusion already there. It didn't work there. Let's just one more duct tape. Oh, it didn't work enough. Duct tape here, and you have this complex model.
It feels like there should be a method where you do a single forward pass and you use some simple loss, like maybe just some reconstruction loss and some kind of simplicity loss in some sense, and it just works. But here is like, maybe you also do top K. That's okay. There is top K SAEs that just do top K, but they're still only doing a single step. But things like this is like has a lot of different losses and a lot of 2 different steps, I think.
I think this meme seems to correspond.
Yeah.
Wow, I found a meme of this type for how LMs compute addition. Okay, whatever.
Also according to so I think this loss is maybe just always.
You also train some of the hidden activations.
Okay, summary. Here it has. I feel like when your method needs like a summary part of the thing. Okay, so. Oh.
Wait, what they do me? We also train some of the hidden activations to be similar on both forward passes. What both forward passes? Forward passes. Oh, okay. So here you only do similarity.
Yeah, they do 2 forward passes and 2 backward passes.
So you only do similarity of the outputs by default in the L minimality. And in some cases, whatever that means, some high probability, I guess, you also have a similarity...
Maybe some of the toy models it didn't work, so they added that.
Yeah, they needed more similarity. It diverged too much, so this was like a grounding. Yeah. We also train some of the hidden activations to be similar on for both. I mean, this could be useful in reinforcement learning sometimes as well, where if you diverge too much from the original policy, then you could do similarity of hidden activations like this. Interesting. Since it may otherwise be possible for ADP to learn solutions that produce the same outputs given different computations. Oh, so this is to...
Okay, so I think so the way I was confused about the way Claude is playing, which I know completely sure is right, is that you you do forward pass. You then do backward pass. You do forward pass to get the outputs and activations, right? You do backward pass to get the attributions. Then you select the top K. Then you compute the 3 losses and you just do an update with a sum of minimality, minimality.
Top K most attributed parameter components.
So this is just some all three losses.
Okay.
This seems similar to like the idea of like the replacement model, but instead of like finding the min like model, you're finding like the most impactful part of the model.
Yeah.
A replacement aren't SAEs a type of replacement model as well? You mean something else?
You know, like
Leo
I mean,
Gauda.
like the attribution graph replacement models.
Yeah, the cross-layer transcoder.
I was thinking of something else.
No,
Yeah.
no. It's not a cross-layer transcoder. Just the replacement model is basically just the idea of like taking the minimum number of like parameters needed to like reconstruct the whole model, I guess. So like it kind of tries like trimming the model and like removes the redundant parts.
Oh,
this one
well,
instead
here-
finds the parts that are like the most impactful instead of removing the redundant parts.
Yeah, and also it's also okay. I'm not sure if I get you correctly there. I didn't check the method you're talking about. I think. So are you saying that in the method you're describing, you basically trim away neurons that are less impactful?
More like you're trying to like basically there's different ways to do it, but basically that's what you do.
So here you do not trim away neurons. You look for all the rank 1 matrices that, if you sum them together, give you the original weights. So you still the number of neurons is still same. It's just different weights that when you sum them together give you the original weights. But yeah, that it sounds in this direction. That's true. In this steering vector, it sounds. It is on some manifold, a sharp manifold. Directionally correct. I also, that's one thing that's used. Thread vector. I was thinking that's also like thread steering vector or something. Yeah, whatever. Technical language. Okay. So they do since it may be possible for the ADP to learn solutions that produce the same outputs given different computations. That is very interesting. That you could split it. I mean, it's still causal. Well, attribution is approximated, so. Oh my god, approximated causality. That sounds horrific. Anyway, well, you have to do approximated causality because sort of causality is intractable, and this is what also causal deep learning people apparently try to do. I'm not sure how they approximate causality. If they also do it through gradients, maybe. Probably. In our experiment, we use batch top k to select fixed number of active parameters for the per batch. Batch top k? That just means per batch.
So they don't seem to have a limitation section, right? Or do they?
Select the fixed number of active components.
Yeah, I feel like this whole method seems super complicated. But apparently,
I remember seeing the post about how this is like a lot better than like SCEs, but this makes me feel like it's similar to attribution graphs.
I think
this is the original.
Yeah.
Like this is the original first proof of concept method, as far as I know. Then these two good fire papers came out, and these were, as far as I know, said that it is something like alternative to essays, basically.
Yeah,
so
I like the idea of decomposing weights, and maybe it's better. It's just this method seems like, so on this paper they just tried on toy models, which is meh, and it also seems like a very complicated methods. Unfortunately, it sounds by what Eric was saying that the other methods are not are still what I would think as overcomplicated, but
do you want to skim the losses in the other two papers?
Yeah. I think this one is also not as complicated as it seems, just explaining a kind of messy way. But
I'll finish now reading the optimizing for simplicity. Yeah. To be simpler than the parameters of the target network. We'd like to penalize parameter components that span more ranks or more layers. So you basically force it minimizing the sum of the ranks of all the matrices in active. So you calculate ranks of the matrices, then sum them all together. How is active component defined?
So loss is on page 35.
Say again?
Oh, the loss is on page 35, appendix. Like the full set of loss.
On this paper, okay, yeah.
Yeah.
What again is active component?
I was thinking that, okay, so if I understand correctly, the problem with the one reason this method requires two steps is that they are doing an attribution step where they do. Okay, so I'm understanding correctly that they do for all do a pass through a data set to get the most top K, most attributed components and remove the other ones. And then they train it a second time on the minimality training step.
They also don't decompose the biases. In summary, we use faithful loss, minimality loss, analysis parameter components that span more ranks or more layers. More layers? What do you mean by more layers? Isn't... Alright, because it's over the whole thing. Isn't penalizing top K, penalizing the... I guess that's when you penalize rank, you also penalize layers, I guess.
Okay, so what Claude is saying, and the reason why this seems overcomplicated, and that it has to be more complicated at least, in that the thing makes sense, that the problem is in the sparse encoders it can be simpler because you can do top K over what you have a notion of what components are useful for the activation, but here what components are useful, like what you don't have which weights are activating or something. You have which weights are causally relevant, and to figure out which weights are causally relevant, you cannot do it with a single forward pass, right?
Yeah. I wonder how when you do the attribution, the grain attributions, how much you get close to the ground truth attributions on some toy models where it's tractable to calculate it. They could have tried to, I don't know. I guess some attribution methods try to do that. At least.
But this seems like if you fix one layer, then like this would be similar to sparse autoencoders. But this is over like all the layers, and it's more like a circuit.
Yeah, no, it's also about weights instead of activations, is the thing.
Oh yeah, that too. But I guess like you are doing some kind of a weight decomposition in like even in sparse autoencoders, right?
Oh yeah, I think you're right. Yeah, because the sparse encoder itself is always a kind of weight decomposition, or like if you think of each feature as a separate thing, you could say it as a weight decomposition.
So Seems like, yeah. Over one layer, like they should be similar, like both this thing and sparse autoencoders.
Yeah, the Atwar method is like different. It has a lot more steps. Well, it has two
No,
steps.
but this one is, yeah, this one is like over all weight matrices in the.
Parametering step sum. Parameterize. Second, for new parameters to collect outputs and activations. Second, backward pass to train the active parameter components to replicate the behavior of the target model on this data.
Also, like they should have a simple example to, demonstrate like their method.
Yeah, they have a toy model there of superposition.
Oh yeah.
I
Right.
think the same selection. Oh, so they have some things here in the discussion session about why this is better than this kind of thing. At least it's better than sports encoders.
Yeah, in the figure 3, I think figure 3 is a visualization of how it works for the toy model. This one.
Yeah. Right. This one.
Okay, I think now I will try to skim the losses in the second two papers.
Okay.
So
also, apparently, it's sensitive to hyperparameters. Say again.
They're decomposing the W into columns, and then they're getting the singular vectors out of this.
They are minimizing the rank. Wait.
The rank.
In this model, ADP successfully learned. No, this is what learned already. So Z1, Z2, Z3, which are the different components. Oh, that's the ground truth, like how the perfect decomposition of weights, which we don't know. So we learn P1, P2, P3, P4, P5, and that's the learned decomposed matrices, which are learned by this weird, complicated machinery, but the most core aspect of it is that each of the components should be have as little ranks as possible. So in this toy model example, it manages to learn a rank for one direction in the superposition correctly.
Also, by the way, Claude is claiming that there is an appendix where they do something closer to what I was thinking that the more simple method would like, and it didn't work. So it's a 2.3 here.
The interpreting language model parameters is not on archive, so I cannot download it easily. Whatever.
So they don't know why this that one doesn't work, basically. Okay, so I was this was something where why was I thinking instead of this top key thing that you just okay, so they have LP norm. So they have a minimality loss and a simplicity loss, and they added that they just do a single forward pass, and that's it.
Yeah, L0 is just number of non-zero components. So I guess if P is less than 1, then it's somehow approximating that. The L0 norm. And minimality would be the number of components. Simplicity would be what would simplicity be?
Simplicity penalizes parameter components that span more ranks, so it forces it to matrices to be as little to have as little ranks as possible.
Okay.
Faithfulness loss trains the sum of the parameters components to approximate the parameters of the target network. So that's like reconstruction loss on the weights, not on the activations.
So this version, instead of doing the attribution step and all that, they just have this minimality loss, this simplicity loss, and they just do a single step and then do a backward pass to optimize it with that loss, which is simpler and it's more like you train like when you train as process coder. But for some reason it didn't work as this as well as this more complicated top K version.
Ooh, okay, so the stochastic parameter decomposition optimizes rank 1 subcomponents instead of full rank parameter components. So is it something like LoRa? Low rank. Yeah, I think this is something like LoRa. That's how you optimize it. Why is it called stochastic? Because they stochastically sample masks. Stochastic reconstruction. Okay. And what does the third paper change? Adversary parameter decomposition. Yeah, I can see how the second paper is very easy if you are, well, not very, but much easier if you already know this paper. VPD. Is this called VPD? This is called ATB. Right. APD, yeah. And stochastic thing is called SPD. Oh no, SPD. Whatever. That's what is VPD? Oh, that's the adversary parameter decomposition. Okay.
Okay, to talk about improving computational cost. Yeah.
Yeah, that's in the in this one they try to do that.
It's just to because the original one, this one that we are looking at today, it was just very expensive. Like it's they're saying that worst case something like O(n) squared, where n is the number of parameters. So yeah, no.
Mechanistic faithfulness, minimality, simplicity, parameter faithfulness. Instead of merely sampling random ablations, which is what SPD did, it searches adversarially for combinations of supposedly unimportant subcomponents that most damage reconstruction. Okay. This is all feels so hacky.
They are saying that
so weird.
Their method suggests that even if it doesn't, that this might solve things that just cannot be solved with sparse encoders, which I think makes sense. Harder to solve.
Joint.
In the other paper, I guess they got rid of this attribution and some kind of a stochastic ablation to get rid of the components. But even that seems like computationally not that good.
Future work will require an explicit clustering algorithm for cases where groups of subcomponents are harder to identify.
Yeah, so this paper is I guess has a nice idea of trying to decompose the things. It does feel like very duct tape idea, but hopefully the next, the Woodfire papers later to do it better, and then that will be pretty nice, I think. And this paper at least came up with the original idea, which is useful, probably.
Yeah. Wait, you have archive for interpreting language model parameters?
I do get the impression that at least the extremely simple version I was imagining is probably just not possible, because you need to do more.
Oh, you're in the PDF, okay.
You need some attribution.
I asked GPT to compare the architectures and losses of each method. So let's see how it will compare it. With features from superposition. I wonder how do they identify the cross-layer distributed things. I wanna see that. Toy model of cross-layer distributed representations. How does it look like? Adding an additional residual MLP layer also performs compressed computation, but now with representations that are distributed across multiple layers. In this model, we again a fixed randomly generated embedding matrix.
For like induction heads, this method is supposed to give you like the looking at previous token plus looking at previous occurrence, something like that, maybe.
The different steps in the induction head circuit.
I don't know. I don't know if those are rank 1.
Absolutely. It's also attention, no? And this is just weights and not attention. Do they look at attention?
Oh, by the way,
yeah.
I noticed something. So this is by Apollo and the other is by Woodfire, but it's still by the same people. Yes. They just went to work on the Woodfire.
Oh, really? Did they?
Yeah.
Yeah, the Lee Sharkey guy is the guy who is in maths.
Yeah, but also like, you know, Lucius Bushnaq and Dan Braun and are also on the lethal authors.
I see. So Apollo poached them. I mean, Goodfire poached them.
Also on the Woodfire paper, it says this.
Oh, okay. I see. It's still the same people doing the same thing. Okay.
Yeah.
Okay. Probably shouldn't have used the pro model. It's thinking too long, but at least it might be better. It's been trying to compare them for 6 minutes already. The methods. Okay, SPD. Instead of learning as low rank as possible matrices, you literally replace it with rank 1 subcomponents. Right? In the stochastic one. Also, the SPD paper. Oh, it's fully open source. Interesting. Parameter decomposition. The whole thing is fully open source and cool.
So what is the stochastic? I guess it's just ablation.
There's many more changes apparently. I'm now trying to run a comparison, but if you so this is the initial summary written down. But yeah. You do rank 1 subcomponents instantly, so you don't have the big matrices, the full matrices that you try to minimize rank on.
The stochastic refers to the random partial ablations, I think, in SPD.
I think so.
Because there is no attribution.
Let's see. Stochastically sample masks.
Oh, something that apparently is more true than was talking with Crow. Apparently, with this method, you don't have with this kind of methods, you don't get feature splitting. Like on the
even for giant LMs.
Yeah, like on it says it's claiming that on the latest one on BPD, even if you increase the increase the number of components, since they are doing a filtering by the number of ones that actually are useful, the number of components that you get, it seems more or less the same, even if you increase the number of.
It sounds like better than SAs then, in this context.
But yeah, we'll have to read that paper at some point.
No feature splitting, highly interpretable. Comparison with transcoders. I am hyped right now.
But yeah, I guess we'll need to look more into the newer papers then, because yeah, this one just was to have a bunch of problems. It was the foundation. It was have a bunch of problems that didn't make it let it work on actual models. I think part of it is too expensive, but also apparently it required a lot of patches and fiddling with hyperparameters for it to work. All that.
Yeah, it's also sensitive to hyperparameters, at least according to the second paper. Here is a table of comparison of the so decomposition in it. ADP is full parameter component. SPD is only rank 1 layer local subcomponents, okay? And VPD is rank 1 layer local plus residual delta components. What the hell is that? Okay, APD. First order gradient attribution forward by heart. Top K selection SPD is 1 small MLP per subcomponent. Reading that subcomponent's scalar in activation. Okay. And VPD is global transformer over target model hidden state. A global transformer. Okay, these methods are much more different than I thought. Yeah, I understand just the APD now. I think you have to read the papers in full to make sense of this. If you want to open this big comparison, here's the GGP link. We've created a table. Explicit exception P rank penalty. Oh yeah, that's how to make it.
I mean, that's assuming GPT didn't make things up, but yeah, they usually don't that with
well, APD at least seems correct. All of that seems correct.
I'll put it on the screen for the recording from it. Yeah. So
and also scroll down to the left. Okay, you have it already. Main losses. That's the last one. Okay.
Okay, so the table is a full component, parameter component, potential is, yeah. And SPD is rank 1 layer local subcomponents. Okay. And BPD is rank 1 layer local subcomponents plus residual delta components. Split plus hop hash clustering. Not sure what that means, but okay.
Yeah, you have to read it, I guess.
Yeah.
But you can see the simplicity mechanism, how you have to have the explicit rank penalty. That's the shut and P rank penalty. But in the SPD, it's architecture imposed that it's always rank 1.
Okay.
So there you don't need any simplicity mechanism anymore, apparently.
Yeah, I mean that feels like it was a weird. I guess it was just to be nicer to optimize, but that was probably not the best.
Yeah. Parameter 5.k behavior reconstruction simplicity. Stochastic reconstruction, layer-wise stochastic reconstruction, importance, minimality. Layered importance plus random ablation. Global importance plus adversarial ablation.
I mean, the thing I'm curious about the third one is what is this activation frequency penalty? What is activation in this context? And why cannot you just train something with that and some set of activations and reconstruction loss? But I guess, yeah, you can also do the ablation part. But yeah, I don't know.
APD directly learns whole, potentially cross-layer mechanisms. Its selector is a first-order gradient attribution, and its hard top K and stack and loss explicitly impose minimality and low rank. SPD changes the primitive to rank 1, layer local subcomponents, and places approximate attribution with learned ablatability.
Okay,
Tested under random partial
stop
intervention.
K is W evaluation over a batch. Okay, that makes sense.
SPD keeps SPD's efficient rank 1 representation, but uses a more global causal importance transformer. They use a transformer to do global causal importance. Okay, it's exact residual parameter accounting. Purchase the yeah, you need that because you have residuals, a residual stream. Searches for worst case ablations. And adds a usage frequency penalty to prevent multiple unrelated mechanisms from being picked. Interesting. Into one rank component.
Okay, so yeah, this top K thing was like, I think I was misunderstanding how it works. I think I was asking, I think I understand better how it works, but yeah, it just was not was kind of a very hacky thing. So they just replaced it by the random partial ablation thing, which makes sense.
Yeah. But this is interesting then. Global causal importance architecture. They just replace scalar input MLPs with a vanilla transformer. Hell yeah! Its input at each sequence position is formed from the target's model hidden activations. Consequently across layers. SPD asks each subcomponent to judge its necessity from its own scalar activation. VPD lets a sequence model use context from other positions and information from all target model layers to decode which subcomponents are necessarily at each token. That sounds like more magic. Maybe what the issue with SPD was that when you just did this local layer-wise thing, you didn't take in account some global computation context or something, I don't know. And that didn't work for LLMs, maybe. Because computations are more distributed in LLMs, I guess. Yeah, I would mind reading the other two to have less than skimming understanding of this. Super cool. But this is cool, I don't know. I wonder... Okay, so I wonder how you could, like, combine it with manifolds. Like, what is stopping you from clustering the weights? Just like you cluster SA features. There is nothing stopping you, no?
Sorry, can you repeat that?
What is stopping you from clustering the weights?
Clustering the weights according
Actually,
the weight components.
Either you cluster the weight components and you might see some manifolds, or you cluster activations that correspond to being run through the different weight components.
Correspond to what?
That get activated with the weight components, however they measure it in the last Goodfire paper.
I feel like we need to understand the measuring. It seems non-trivial and maybe the important part of the third paper, like the activation thing.
Yeah.
Because there is no, intuitive notion of how much sort of weight component is activated or anything. There is some. That's why you and the other things you need to get causal effect on it on the output or whatever.
Let's see. How do they measure the component consistently activates on punctuation characters? If GPT can extract it, I want to extract concrete quote. Extract concrete quotes for how do they exactly quantify the component consistently activates on X punctuation characters, for example. But I like that all of it is open source, all the papers. So we can play with it technically. And it seems to be updated literally 2 hours ago. So it's very in development. Okay. I wanna compare it with essays. I guess they did a lot of comparisons with essays that I had in mind. I just asked the LMs for that to extract the comparisons. You also wanted me to ask the LM about something.
I don't remember.
Like these are some of the notes I've written down. You meant some things from this? Maybe. I might try to ask, but first I wanna see how exactly they quantify the component consistently activates on XYZ characters. But it's cool. Like I like to see more alternative to essays. Also, by the way, there is like some. It's polytope. There is some paper trying to generalize the land shapes. I don't think it was polytopes, it was something else. I wanna see that. Find it for me. Let's search. See if it can find it. Okay, is this one done? Yeah, they the quantify activates in 2 different ways. Oh. Also importance. Learned value for subcomponent C matrix patch item 2 estimates whether ablating that subcomponent would affect the output. Oh, so they do like ablating. If you ablate it, does the model stop talking about, I don't know, Golden Gate Bridge cloth? Something like that. So that's how they quantify it. That makes sense, causally. Or subcomponent activation, a local dot product style score. How strongly the current hidden state interacts with that rank 1 subcomponent, even when it's not ultimately causally relevant. Okay. Yeah, that's reasonable. Either similarity. Oh my god, I really dislike the fire. Ah, there's a markdown version. Good. That's useful. Causa importance. How we train a causal importance function to predict how ablatable each component is. Right. Causa is trained to output a value between 0 and 1 that tells us exactly how important a particular subcomponent is on a data point. It tells us if the subcomponent is necessary, required, or used on that input. This is the perfect definition of active. However, it is not a local measure of a subcomponent's activation. A subcomponent with small causal importance value might interact strongly with the activations at a layer only for its effect to be suppressed later by others. For a more local measure, we use the next definition. Subcomponent activation. We define the subcomponent's activation as okay. Dot product between the hidden activations and the weights. How much the activations interact with the hidden subcomponent? Okay. Due to superposition, there will be more interactions in general direction. Causal important interactions. Could you combine those two together though? Maybe. No feature splitting. I want to see that aspect now. The reason why it doesn't suffer from feature splitting is that the key reason for this is that subcomponents marked as causally unimportant are required to be ablatable in any combination. That's marked as causally unimportant. Model therefore needs to be robust to variations in parameter space along the directions of the subcomponents for patches, sequence positions, not just the ones on which they are causally important. Without this constraint, the decomposition might be able to invent overly narrow. They have some ways. They have importance minimality, which just seems to suppress feature splitting, I guess. With stochastic or adversarial masking, many of the subcomponents not marked as causally important will be turned on as well, making the resulting outpactation vector both too large and point in the wrong direction, thus ruining the reconstruction. Ah, I see. I see, because you have the sum, right? Because you have to sum it all together. Then feature splitting, you would just get duplicate same direction, right? Therefore, if you would do feature splitting, you would destroy the reconstruction in this context. There is no summing global constraint in SAEs. So SAEs can learn two directions that are the same in different parts of SAE. Why here you cannot do that, or you probably don't do that if the model learns correctly, because it all has to sum to the whole model. That's my understanding now. All right.
Do we just end the recording here, because I feel like we already mostly.
You could do that. Yeah, I'm now gonna try to ask the idea of. I'm gonna ask ChatGPT if my idea is slow or not about clustering the activations computed from the rank 1 components.
Yeah, I
Find
think we mostly
manifolds in unsupervised
this
way.
whole thing is kind of, yeah.
Did you find something while skimming now, or?
No, not really. I mean, I was looking at some things, but not. I think I just need to read the new papers more than this one.
Yeah, okay.
Like, this has some interesting things about how it relates to other methods, to person encoders and all that, and how it's not the same kind of thing it's related, and how, that kind how you are trying to think what can we consider logic compression algorithm automated to compensate the decision attribution data sets, and this is compensate description of the causal process that network-based activations. I like this thing of the paper that says that the amount of mechanistic understanding about neural network is quantified by how much you can compress proofs out the model's behavior. That seems like a neat theoretical view of how well you are doing Mech Interp. But yeah.
Can be measured quantified by what exactly? How much it compresses about the network behavior?
Yeah.
Okay.
That sounds neat.
Yeah, like
I don't think proofs is maybe the wrong thing, because you can also have, although this is obviously much harder to formalize, but you can have it compress heuristics out the network behavior. But yeah.
Like in the frame I like the most, you want predictive power and explanatory power. So predictive power would be, I guess, the proofs about the behavior, so you can actually predict the behavior to some degree. And explanatory power includes simplicity. So the more simple your model is, the more compressed it is, often.
Power is just simplicity.
Okay, say again.
I think explanatory power is just simplicity.
I think it includes more things. Yeah.
I think the more things
Well,
probably
a lot of
the simplicity.
A lot of the attempts at AGI formalisms, there's like, I found at least 3 of them, which are basically all you need is predictive power and simplicity.
Yes.
But I think it's good to, like, I don't know, falsify a bit, it sounds good. For example. Like, you don't, but I don't know.
I think
when I rabbit holed into
falsifiable becomes like theories are only falsifiable with respect to other theories, but there is no. I think it ends being simplicity in disguise. But I think I should just stop. If I'm going to start talking about that, I should just stop the recording, all that. But maybe I'll look a bit at the paper in case there is something more about the paper to talk about. Also, anyone else want to say something about the paper or something before I, finish the reading group and start the recording, all that? Doesn't seem like people have takes, I guess.
Okay, let's see.
I didn't know about this quant identification thing, by the way.
Okay, looks like ChatGPT told me my idea is not slop. Good.
So this is their.
Therefore, that definitely is a proof.
This is
Not
related to stuff
potential.
you were talking about. The quantas things is about they are doing clustering of gradients of the loss.
Wait, what?
The quant identification thing, which is related. I didn't know
Visually
there was a
identify
thing.
quanta, where quantum is defined as indivisible computational model that, for example, retrieves effect, implements an algorithm, or generally corresponds to some basic skill possessed by a model. I would call that an atom, not quanta. Whatever. Maybe. This definition reflects aspects of what our work defines as mechanism. Through our definition is formal. To identify quanta in language models, they cluster the gradients of the loss. Gradients of the loss? What? Why? With respect to the parameters. This shares the intuition with our work that different gradients reflect different active mechanisms. However, clustering gradients does not decompose them. Let's train SAEs on gradients then. By training parameter components to be sparsely attributed, our method implicitly trains parts of our parameter components to align sparsely with components gradients. With components of gradients. Yes. Cluster gradients. Okay. Yeah, I think this is still different. I don't know. Maybe not. Section 3.1. It's in the original PDF, right? Yeah. Wait, what? But I do it in the superposition thing.